Alright, Chapter 6, Algebra 2. Polynomials. Now, this is kind of an ugly looking generic polynomial. And what I want you to see here, P of x represents the fancy notation, function notation for y. Y equals. That's pretty much what you have right here. We have some number called a coefficient that's being multiplied times a power of x. What I want you to realize from this ugly definition is that the exponents keep getting smaller. So in other words, we start with the highest exponent and we keep getting smaller. Eventually we get down to 2 and then x to the first and then x to the 0, which we know that x to the 0 is really the number 1. So there's no power of x on the end, technically. So that's a generic looking form. A specific form would be something like this. Y equals 2x to the third minus 5x squared minus 2x plus 5. This is called the standard form of a polynomial. The first term is called the leading term. From the leading term we get the leading coefficient, which in this case happens to be a 2. From the leading term we also get the degree of the polynomial, which happens to be the highest exponent. So this is a third degree polynomial. The cubic term, which happens to be, in this case, the leading term, is 2x cubed. The quadratic term, negative 5x squared. The linear term, negative 2x. And the constant term at the end is 5. Now I do want you to look at the chart in the book for the degrees. And let me show that to you. We can classify a polynomial based upon two different things: the degree of the polynomial and also the number of terms. So for instance, a 0 degree polynomial is just a constant. It's a number like 6. A degree 1 polynomial is called a linear polynomial, or the linear is the cute name that we use for it. An example would be something like x plus 3. Quadratic has a second degree, cubic has a third degree, quartic has a fourth degree, quintic has a fifth degree, and then we don't have any cute names for the degrees after that. Those would be the only names you'll be responsible for your degrees. Number of terms. A single term is called a monomial. Two terms would be called a binomial. This one has 2 terms. This one is a quadratic monomial. So we can call them linear binomials, constant monomials, cubic, but it has 3 terms, also trinomial. This is a quartic, but it only has 2 terms, so it's a quartic binomial. Now, if you have more than 3 terms, we run out of cute names in terms of the terms, and so we call them polynomial of 4 terms. Or polynomial of 5 terms, or polynomial of 17 terms. But we run out of those cute names, and so we just resort back to polynomial. So you'll have to decide if something is based on its degree. You'll have to name it based on its degree and also on the name of the term. So be familiar with those names. So for instance, write each polynomial in standard form. You'll notice that this is not in standard form because it has to be in decreasing order of exponents. So we'll start with the 5x to the fourth, and then we'll list out the second term, the minus 7x. That's the first thing we needed to do. Second thing we need to do is classify it by degree. So this is a quartic. 2 terms, that would be binomial. On the second example, we can start with the highest degree. So that would be 3x to the third. And make sure you add any like terms. I see a plus x squared. Minus 4x and plus 2x, those are like terms. They need to be added together. That would give me minus 2x. So that's in standard form. This is a cubic because it has a third degree. And because there are 1, 2, 3 terms, it is a trinomial. Cubic trinomial. What would help me graph a polynomial? Well, there are a couple things that you need to know. You need to know about end behavior. You also need to know about zeros, a fancy term for x-intercepts. And you need to know something about the multiplicities of those zeros, which we'll talk to you about in a minute here. Or I'll talk to you about in a minute. End behavior. What is end behavior? End behavior is the I should say the direction at the extremes. Direction at the extremes. Far left on the graph and far right on the graph. We want to know what's going on. Polynomials will either go up or down forever and ever and ever. So here's a couple examples I want you to look at. This particular polynomial goes up far on the left and up far on the right. So when we list out its end behavior, we write almost what looks like a coordinate, and we use arrows indicating that it's going up to the left and up to the right. I'll tell you how I know that in a minute. Okay, based on the equation. This one, down, down. Obviously you can see far to the left, far to the right, both going down. This one goes up on the right but down on the left. This one goes up on the left but down on the right. So how am I able to look at these equations and pick out what's really going on here? Well, it all has to do with the leading term. The leading term is the only thing you need to pay attention to. So in this one, it's x to the fourth. What do you need to know about x to the fourth? Well, if this is the leading term, I look at the coefficient, the leading coefficient. The leading coefficient in this case is a 1. It's a positive 1. Any time you have a leading coefficient which is positive, that tells me that the right end behavior is up. So this has the right end behavior has everything to do with positive leading coefficient that goes up, negative leading coefficient down. Always decide the right end behavior first. Next, I look for the degree. If the degree is odd, then left end behavior is opposite of right. Obviously, if the degree is even, then left end behavior is the same. In this case, we had an x to the fourth for our degree. That's an even number, so I know that it is the same as the right. So, leading coefficient tells me whether the right end behavior is up or down. Degree tells me whether the left end behavior is the same or opposite of the right. Always decide on right end behavior first. So let's take a look at these examples again. Leading coefficient is -1. That means the right end behavior is down. Degree is even. That means the left end behavior is the same. Leading coefficient is 1. That means the right end behavior is up. Odd degree means the left end behavior is opposite of the right. Leading coefficient is -0.3. That means the right end behavior is down. Left end behavior, or its odd degree, means that the left has to be opposite. So that's how we decide whether something, what its end behavior is. Okay, now, finding zeros or x-intercepts. We know that x-intercepts have a y value of 0. So what are we going to plug in here for y? Of course we're going to plug in 0. Now, we should know from chapter 5 how to solve this, right? It's already in factored form. That's beautiful. So I set each one of the factors equal to 0, and I solve them. Not to say that this is all that hard. X is equal to -1, or -2, or -3. You probably already knew that. Those are my x-intercepts. Or you could use the term zeros. You're going to see that term zeros a lot, so you might as well get used to it. Graph the above polynomial. Okay, so we had y equals x plus 1, x plus 2, and x plus 3. Well, I need to know the end behavior. In order to know the end behavior, I need to know the leading term. Well, it's pretty easy to find the leading term without having to multiply all this stuff out. Take the firsts of every parenthesis and multiply them together. X times x times x. So my leading term is x cubed. It's got a +1 for a leading coefficient. That means the right end behavior is up. It's got an odd degree, therefore my left end behavior is opposite. When we go to graph this, we know our zeros. We found our zeros a few minutes ago at -1, -2, and -3. So it's crossing through or touching the x-axis in 3 spots. -1, -2, -3. The next thing I want to do is I want to take my end behavior and I want to attach it to the outermost zeros. In other words, I'm not going to touch that one in the middle, but I am going to go to the outermost zeros and I'm going to attach my end behavior. For reasons which we will explain later, this graph goes up and then comes back down. Now, how far up and how far down does it go? I'm not really going to get into that with you right now. We're not going to be deciding how high or how low. This point right here is called a relative maximum. Now, it's not really a maximum to the graph because the graph continues on up forever and ever and ever. But if you were just to look at this piece of the graph right here, you would call that a maximum. So we call it a relative maximum because it's at the top of a little hill. So at the bottom of a little valley, that one's called a relative minimum. And I'm not going to ask you what the relative maximums and minimums are, but I am going to ask you questions like that, like between which two consecutive zeros would you find a relative minimum? Whoops. So obviously we would find it between -2 and -1. Between those two x values, you would find the relative minimum. Now, I'm not asking you what the relative minimum is. Without plugging in a lot of different points, we're not going to know. We're not going to be able to figure that out. So, unless we use some calculus, and we're not going to do that. Okay. Now, the next topic that I didn't talk about yet is called multiplicity, and that is the number of times that a factor occurs. So, in this particular example of a polynomial, we have y equals x plus 2 to the third power and times x minus 1 quantity squared. X plus 2 you could see occurs 3 times according to the exponent. I wouldn't write it out 3 times because I don't need to. So we could say that -2 is a 0 with multiplicity 3. We can also see that x minus 1 occurs as the factor twice. Since x minus 1 occurs 2 times, we can say 1 is a 0 with multiplicity 2. So, in other words, if I had a chart like this and I said, what are the zeros? You would say that -2 is a 0 and the number 1 is a 0. Now, how often do they occur? What's their multiplicity? Well, this one was a 3, and this one was a 2. Now, how does that show up on a graph? Let's suppose I was supposed to graph this thing. We know that we need our zeros. All right, we got that, -2 and +1. We need our end behavior. And behavior, let's see here. We want the firsts. Now be careful here. We have x to the third power times x to the second power. So what is x to the third times x to the second? That's right, x to the fifth. Leading coefficient is positive, therefore the right end behavior is up. Degree is odd, therefore the left end behavior is down. So -2 we have an x-intercept, +1 we have an x-intercept. We're going to go to the outermost zeros and attach the end behavior. Outermost zeros and attach the end behavior. The big question is what happens in between? What happens in between? What's the difference between odd multiplicity and even multiplicity? Even multiplicity bounces off the axis. Odd multiplicity cuts through the axis. So which one of these is an even multiplicity? Obviously, it's this one right here. So that is the 0 that's 1. This is going to be the one that bounces off the axis. So in other words, in my picture, I'm going to make it come back up. Now the other one's an odd multiplicity, so it will cut through the axis. So that's a basic looking picture of what's going on here. Just a sketch of the graph. This indicates my right and left end behavior. I know the zeros of the function, and I know that this person thinks that it's an even multiplicity here and an odd multiplicity there. We'll practice our graphing tomorrow.